This episode of the HVAC School podcast is made possible by the Carrier Corporation, as well as Carrier Enterprise Florida. This episode is also made possible by Testo. Testo, makers of high-quality test instrumentation for the everyday technician all the way up to industrial applications and many, many more applications. You can find Testo products by going to TruTechTools.com, and you can get a great discount by using the offer code GETSCHOOLED at checkout. We also have a new sponsor, Danfoss and the Danfoss family of applications, the Danfoss Toolbox, as it's known. And the Danfoss Toolbox has lots of great applications, some of them specifically for Danfoss products and some of them very general, like the refrigerant slider app. You can find them for free on both Android and on iTunes, or you can save searching by just typing in danfoss.com/cool apps.
Less like a cowboy of HVAC and more like your annoying cousin Randy, Brian Orr.
Yes, this is the HVAC School podcast. I almost forgot the name of my own podcast when I started my intro. I'm like, it's the HVAC. What's that stand for again? I'm Brian, and today we have almost a clickbait seeming episode. Like how to check a charge without even connecting your gauges. And when Jim first brought this up, I was like, come on, you're not actually advocating for not connecting gauges. But no, really, he is advocating for connecting your manifold much less than we normally do. And it's interesting because it's the type of thing that we use it as an insult, right? It looks like that guy didn't even connect gauges to the system, or he probably didn't even connect gauges or whatever. But really, Jim is going to tell you reasons why he thinks we connect gauges far, far, far too often to systems. And truthfully, by the time it's all said and done, I was won over to at least a certain extent. So this is going to be a two-part series, and here we go, Jim Bergman. All right, so today we're talking charging, right?
Actually, I was going to do sort of like checking the charge without gauges where my brain was at.
All right. Why don't we just do whatever you want, Jim?
Why don't we do whatever I want?
How about that for once? Once in your life?
Yeah, I think so.
Sounds good. So checking the charge without gauges. I guess I want to start this conversation by giving a disclaimer, because when people hear that we're doing an episode on checking the charge without gauges, what I'm not saying, maybe you're saying this, but what I'm certainly not saying is that people should stop connecting gauges to systems. Most cases, you're probably going to still need to connect gauges to systems. But there are some cases where connecting gauges to systems may not apply. That's my stance on it, unless you convince me otherwise through this episode.
All right. Well, you probably should connect gauges to systems you've never connected them to before. But once you've connected them once, or somebody at your company's connected them once, there's no reason that you ever need to connect them again. That's my stance on.
Ever, Jim?
Unless the testing dictates otherwise. Otherwise, okay. Yeah, ever. Okay. Forever.
I worked at a very large company before starting my own business, and now my business is a good-sized company. So I don't know that I would trust the readings that somebody else even took. That still concerns me a little bit. Like, all right, so let's just start here. And this isn't the right place to start, but this is just where I want to start because it's where my brain's at. And I want to at least exact some control over my podcast still. I'm thinking, okay, aren't there cases where you could be running, let's say we have a piston system, and you're running low superheat or zero superheat, but your system capacity would still show as being in the range of what you'd be looking for from a delivered capacity standpoint. What am I missing there?
Well, what you're missing there is basically you're diagnosing the entire system off superheat and subcooling, and that's a big part of the problem. And unless you understand what the pressure should be, then you don't understand what you do for a living. And that's where most people fall flat on their face. In fact, I've gone out to a lot of classes and a lot of places, and I say, before we hook up the gauges to the system, what are the pressures going to be? And people look at me like deer in the headlights. I'm like, well, if you can't tell me what the pressure should be, what difference does it make what they are? Because temperature directly correlates with your saturation temperature, right? You agree with that?
Yes.
Okay. And saturation temperature is the driving force for moving heat out of the house. So when you think about an air conditioning system, you got to go all the way back to the basics, right? Heat transfer is a function of three things: time, temperature difference, and turbulence. And the temperature difference in this case is the major driving force that drives the quantity of heat into the coil that we're going to reject outside, right? So the larger the temperature difference is, the faster the heat transfer, the smaller the temperature difference is, the heat transfer goes down, right? So it's that pressure is probably one of the most important things when we come to quantifying system performance. If you just look at superheat or you just look at subcooling, you're only seeing a small part of the story, because what if you have perfectly fine superheat, but your coil's 28 degrees? Is that an issue?
Of course.
Of course it is,
well,
right?
Actually, it depends on the type of system, obviously, but yes.
We're talking
straight
cooling, air conditioning for this conversation. We could do refrigeration's the same principles, but when I talk about freezing or not, we're talking about straight cooling here. So let's start there, with a conversation. I don't know if you got any questions, but I can go into some details, or you can ask me some questions.
Okay, so we'll do that, but I still want my question answered here, which is obviously I understand that you have to take superheat, subcool, suction pressure, head pressure, and then a battery of other tests you could do in addition to that. But to me, superheat, subcool, suction pressure, head pressure are all contingent on connecting gauges. So that's where I want to start is, what am I missing there?
Okay, so let's just start with a standard 10 SEER or 12 SEER, I don't care. 10 SEER is really popular. A lot of guys just know the readings off the top of their head. So let's just start with a standard, or 10 or 13 SEER. I don't care. We could start with a 13 SEER 410A system. What's your preference? What do you want to talk about?
Let's do a 13 SEER 410A system.
Okay, so 13 SEER 410A system, right? All right, we've already talked about time, temperature difference, and turbulence. And let's just cover a couple things real quick right there. So first of all, heat transfer takes time. Right? If I take a lighter and I light the lighter up and I take my finger and I go through the flame in the lighter, I don't get burned, right? And as long as I'm just going flicking back and forth through the lighter, I don't get burned, and I don't even feel the heat transfer. And that flame's 1,000 degrees and my finger is, 88 degrees, 90 degrees. And I have this huge temperature difference, yet I don't feel heat transfer because there's not enough time for the heat to transfer. If I slow my finger down real slow going through the lighter, where I hear some sizzling and crackling and stuff, you can feel massive amounts of heat transfer, and you move your finger out of the way very quickly. So the first thing we got to realize is we got to have enough time for the heat to transfer. And if the heat transfers too slowly, then eventually your finger and the lighter get to the same temperature, right? That's when your finger's crispy and falling off because your finger got up to the same temperature the lighter was. And again, the heat transfer stops. So there's a definitive point there where if we transfer the air across an evaporator coil too slow, the air is going to get down to the evaporator coil temperature and heat transfer is going to stop. And if we zip by too fast, we're not going to have time for the heat to transfer out of the air. Okay, so starting with those two things. Now, the second thing is that we have a temperature difference. So we talked about that. The rate of heat transfer is dependent highly upon the temperature difference. And then we've also got turbulence, and that's like the design of the coil and things like that. You got to think about, as the air is going through that maze of fins and pipes, and we got expanded surface area and zigzaggy fins, and there's no direct path through. That's the turbulence we're talking about as the air travels through the coil. So an increase in turbulence also increases the residence time in the coil, and we get more heat transfer, right? Because we're making a more complex path for the air to travel through.
It's just that the air's not going directly through. The air is making, in many cases, multiple passes. I mean, it's hitting and it's bouncing around and circling around and all that. So
Exactly.
it has more dwell time on the coil surface then.
Exactly. Yep. And again, if we go too slow, the air temperature gets down to the coil temperature and we start to lose efficiency, because everybody forgets, I think, in our industry, that heat is a quantity. It's when we're transferring 30,000 BTUs, that is a physical quantity of heat. Heat is not the same as temperature. Temperature is the intensity of heat. It's how fast the molecules are vibrating, where heat, BTUs, are a measurable quantity. There's when we talk about the amount of heat it takes to raise 1 pound of water, 1 degree Fahrenheit is 1 BTU. That is a quantity of heat. When we talk about air, while water has a specific heat of 1, air has a specific heat of 0.24. So it takes 0.24 BTUs of heat to raise 1 pound of air, 1 degree Fahrenheit, right? And when we talk about air, we're really not cooling the CFM of air going across the coil. We're cooling the mass of air going across the coil. So when you go back to your psychometric charts and we say, okay, standard air has a weight of 0.075 pounds per cubic foot, what that means is, first of all, that's dry air. That's 68 degrees, 0% relative humidity air. But if you multiplied that 0.075 times 400, you would get 30 pounds per minute per ton. Okay? And I'm going to recommend a text. For those of you that so many guys in our industry, they have no formal training, or the formal training they got was substandard. They spent a couple days in a classroom. If you haven't ever bought a copy of Refrigeration and Air Conditioning Technology, it's by Whitman, Johnson, and Tomzik. You can buy them used on eBay. Even an old book is better than no book.
The good old racked manual.
Yeah, I taught out of that for 13 years. I've actually proofread several other texts over the years. Refrigeration Air Conditioning Technology is by far the best text out there. And a lot of what I'm talking about today is actually out of chapter 40 in that textbook. It's called Typical Operating Conditions. And that's where I sort of had an epiphany with this when I was in teaching, because so many of these chapters, chapter 1, 2, and 3, are like the science behind what we do for a living. And then, we get into evacuation recovery, I think, in chapter 4, and they get into chapters like chapter 40, and it starts tying some of these things together. And if you don't have a text, I'd highly suggest you pick up one and start studying that text, because it will help your career tremendously. And it's a great reference text to have on your truck.
Also, if you pick up the racked book, it also helps with your exercise program, because the thing weighs like 45 pounds.
Oh, yeah, absolutely. Absolutely. Yeah. It is a heavy old textbook, but it's a great text to have, and it's much easier to read than like modern refrigeration, things like that. It's at a high school level, but I'll tell you right now, it's not high school level information. It's also college level. It's just written at a level that's easy to read. And for most HVAC techs who don't like to read and get most information from podcasts,
the best way. Yeah. The best way to get all your information is just to listen to HVAC School. You never need to read.
Okay. Yeah. Well, if you need to read at some point because you go deaf, you can pick up a lot with Refrigeration Air Conditioning Technology. But going back to this, I believe it's chapter 3 in that text. There's a formula. It's Q equals mass times specific heat times temperature difference, which that's like the formula of all heat transfer. Q is quantity of heat times the mass, so times 30 pounds per minute per ton. Or if you took that times 60, right, you could say it's 180 pounds per hour. And you start multiplying that out, you can actually determine what the temperature difference of the air would have to be in order to transfer the correct amount of BTUs, because we know the specific heat of air is 0.24, we know the mass of air, and we know the quantity. If we say 1 ton, and we can divide that out, and we can actually figure out, we'd probably need I'm just going off the top of my head here, but I want to say about a 28 degree temperature difference to move all the heat to sensible heat on the air conditioning system. Now, a portion of the heat is always dictated to latent removal, typically like 0.75. So, you say 0.7.
Moisture, humidity. When we say latent, we're talking about moisture and humidity.
Moisture and humidity, correct. So if we're to take 0.75 times, I'm pulling out my iPhone here. I want to say it's going to be about 21. 0.75 times 28 is 21 degrees. Yeah. So I just didn't want to get the math wrong. So about a 21 degree split across your evaporator. That's actually where that number comes from. If you want to go back to, when we talk about a 20 degree split across an evaporator, well, that's where that number comes from. Now we know that can be anywhere from 16 to 24 degrees with a humidity load, but that 20 is based upon 75 degree air at 50% relative humidity with a 95 degree outdoor air temperature. So let's go back for a second. Now we know that there's some fixed quantities here. So here's the first thing we need to know. For an air conditioner to move the turbulence is fixed by the coil design. Okay, would you agree with that? And obviously we can have multiple row evaporator coils, and we can have, all these different things. But when it really comes down to the engineering of an evaporator coil, the physical engineering, because here's what everybody's got to remember. Every single manufacturer is trying to design for optimal efficiency at whatever SEER they're designing for. If we're talking about 10 SEER or 13 SEER, you're talking about how can I make a 13 SEER piece of equipment with the least amount of materials, the least amount of refrigerant, and operate at the most efficient design, right? Everybody's got to hit the same target. They have so many amps of power per BTU of energy moved, and that's what they're engineering for. So when it comes down to physics, if everybody's designing to hit the same targets, the quantity of heat they're going to have to remove is going to be the same. If everybody's designing for an AHRI standard, which almost every air conditioning coil is designed for 30 pounds per minute per ton. And I don't care if you say, well, my system's a nominal 350 and mine's a nominal 450 and mine's a nominal 400. The coil's all designed the same. It's designed for a nominal 400 CFM per ton. More or less airflow is just going to make the coil perform differently. But there's only a couple sets of tables to design coils. They're based upon 30 pounds per minute per ton of air across the coil. If everybody's designing for the same thing, and we know that we can only make the coil so restrictive because we got half an inch of total external static pressure to work with. we need static pressure to make the air move through the ductwork. So we got to have a static pressure left over to move air through the ducts. Everybody's going to move the same quantity of heat. Everybody's sort of bound by the same friction. So we got the velocity going across the air. We know if it goes too fast, it's not going to transfer the heat. If it goes too slow, it's not going to be efficient, right? So everybody ends up with very similar velocities of air going across the coil. They end up with very similar coil designs for that tonnage because they can't have too high static pressure drops. And guess what? That means they also have to operate with very, very similar design temperature differences. So we're going to talk a little bit about DTD's, design temperature difference, or you might also hear on the high side, CTOA, which is condensing temp over ambient. And those are two things I want to talk about in depth this morning when we talk about checking the charge without gauges. And I'm going to challenge you, Brian, because you deserve to be challenged.
Okay, thank you.
Because you are challenged, but
right, in many ways.
Additional challenging would be a good thing for you. Let's just back up. So let's just say we got 75-degree return air. Okay. Now there's two things we got to remember when we're talking about an air conditioning system. The split, which is the difference between the supply air and the return air, is going to vary with the latent load, with the humidity removal. The more humidity we have to remove from the air, the lower the split's going to be. So at very high.
Let me stop you there. Hold on, because a lot of people, this is a lot of confusion. I've got a lot of questions about this. Some people, when they say evaporator split, they mean the difference between the evaporator temperature, so the actual evaporator saturation temperature / boiling temperature of the evaporator, and the return air, right?
Okay, yes. That's what we're going to call design temperature difference.
Okay, so we're going to call that
design
DTD.
DTD. So it's how much colder is by design is the evaporator than the return air. That is a fixed number. Okay, by design, that number is always going to be fixed. Now,
hold on, I wasn't done. I wanted to find another term here. Okay,
all right.
So what a lot of people call evaporator split, we're going to call design temperature difference. And then, so we're going to use the terms temperature split, air temperature split, and what a lot of people would call delta T. We're going to use those synonymously. So we're talking about the difference between the return air temperature going into the evaporator coil and supply air temperature going out.
That is right? Split. Yep, split, or we're going to call that delta split. T. Yep, either one.
Okay. And
design temperature difference is how much colder is the evaporator than the return air. And CTOA, or DTD for the outside unit, is how much hotter is the condenser than the outdoor air, right?
Correct.
So just to clarify this, for those of you that don't have some formalized training, heat only travels one direction, from hot to cold. So in order for heat to travel into the evaporator has to be colder than the return air. So heat from the warm house travels into the cold coil. And then what the compressor does is it raises the boiling point, or the pressure of the refrigerant, to raise its corresponding temperature, right? So we raise the pressure, raise the temperature, so that it's hotter than the outdoor air. So the heat travels from the hot condenser into the cooler outdoor air. And even if we're talking 100-degree air, the condenser has to be hotter than the outdoor air. It's going to be a fixed amount hotter than the outdoor air to reject that quantity of heat. Okay. And when we say fixed, design temperature differences will vary, but maybe by only a degree or two. I mean, these are very, very small changes, because the other thing you got to remember is our compressor. And when we talk about compressors, again, I'm talking full load here. So you could talk about part load. We can talk about those things in a minute here. But when we talk about a typical compressor, it moves a fixed volume at a variable mass flow rate. In other words, if it's going to pump 10 CFM, it's always going to pump 10 CFM. But as the density of the refrigerant gas changes, the pounds of refrigerant moved through the compressor will change. If we put in a higher suction pressure gas, it's going to increase, it's packing more in there, just like a turbocharger does on a car, right? When we raise the inlet pressure, we're packing more in the cylinder, and that's going to increase the mass in that cylinder, the mass flow rate, and it's going to take, increase the amperage of the compressor, and we're going to be doing more work. Not significant increases in amperage, but a little bit of increase in amperage, because you also got to reject that heat on the high side. If we held a constant condensing temperature, like if we had a water-cooled condenser and we could hold that condensing temp the same, as we increased our suction pressure, our amp draw would actually go down, because the work the compressor is doing is creating the pressure difference. And you would see, if you looked at a compressor performance chart, you would actually see that amp draw going down as the pressure difference across the compressor goes down, right? That's its job also.
Okay, so the compressor moves. I got to just jump in there because you're just like a freight train and you're hard to stop.
sorry.
The compressor moves a set volume of refrigerant, but as we increase or decrease the density and therefore the weight of the refrigerant, that changes the amount of refrigerant that the compressor is actually moving, even though the volume is remaining the same, the actual space inside. So the inside that compression chamber, it's compressing to a particular specification. That's not changing, but the density then changes the amount of actual refrigerant that's being moved. Is that a good way of restating that?
Yeah. Think of it as a piston has a fixed volume that, when the piston goes on its downstroke, you have a cylinder that it only goes down so far and it only goes up so far. So it only moves so much volume each time it moves. And if we have really dense gas, it's going to have a high mass flow rate. If we have really light gas, it's going to have a low mass flow rate. So it's a fixed volume at a variable mass flow rate. And it's the same thing with a fan when we talk about like a PSC fan. A fan moves a constant airflow independent of the air density. So if it's going to move 400 CFM, it's always going to move 400 CFM, but it could be moving 28 pounds per minute, or it could be moving 31 pounds per minute as the air density changes. So same thing, but it's a very fundamental and very important thing to know when it comes to compressors and fans, how they work. So
Got it. Okay.
All right, cool.
All right, so this is our tooltip corner, and one thing that you need to know if you're going to be checking charge without connecting gauges or without connecting a manifold is you need to know your PT relationships. You need to know your pressure temperature relationships. So when I first started in school, I actually would keep a PT chart in my pocket, an actual chart that shows the pressure temperature relationships, specifically the saturation temperature at a given pressure or the saturation temperature at a given pressure. So vice versa. I might have said the same thing there twice, but you get the point. Either or. And so what does saturation mean? Saturation means mixed state. It means it's mixed, both liquid and vapor. So both liquid and vapor are present at the same point at the same time in the system or in a tank or whatever the case may be. So one practical application of this, even on a system that's not running, is you take a tank of R22 off your truck, say, and you measure the temperature, the ambient temperature around the tank, and then you plot that up. You will know exactly what the pressure of that refrigerant will be inside that tank. So essentially we use saturation in order to get data about what's going on. So if we know that something is in a mixed state, so we know that liquid and vapor is present, and we're trying to identify what the refrigerant type is, we can use a PT chart to at least approximate what type of refrigerant is in there. So I've got my free Danfoss refrigerant slider app open on my iPhone here. So let's say that the ambient temperature is, I'm just scrolling up and down on this, let's say the ambient temperature is 75.6 degrees Fahrenheit. We're going to be real detailed on that because you can do that here on this app. 75.6 degrees Fahrenheit, R22 is going to be 133.26 psi inside, if we know that it's mixed refrigerant, meaning that we know that there's both vapor and liquid in the tank, which you can tell just by picking it up, really. But if there was only vapor, well, then the pressure could begin to drop in the tank. But if there's a mixture of liquid and vapor, it's going to be at that pressure. If it was fully liquid, then you'd have hydrostatic pressure and the tank would explode. So we know at 75.6 degrees Fahrenheit that if it's R22 in a mixed state, it's going to be 133.26. So you hook up your gauge to it and you read 133.26. At 75.6 degrees Fahrenheit, you know you've got R22. I mean, it could have a little bit mixed in there or something that's very close to R22, sure, but you can be fairly confident of that. Now, let's say we hooked up to it and we saw that we had 223 degrees or 223 PSI. Well, then we would say, okay, we have something else mixed in there that's not the same refrigerant. But we use this most often when we're diagnosing a system. We're looking at our gauge and we're seeing our pressure, but then we're looking right down the line and we're looking at our saturation temperature and we're comparing that. In the case of what Jim's talking about, we're comparing that to indoor temperature to get our design temperature difference. We're comparing that to the outdoor temperature to get our condensing temperature over ambient or CTOA. And so we need to know the saturation temperature. The challenge is that if you're not using a gauge manifold, we're so used to using the gauge manifold that we're almost lost. We don't know what to do. So when you're checking a chart without a gauge, you need to have a PT chart that just works. And so I suggest the Danfoss refrigerant slider app. It's a great app. It really just replaces the need to ever have a PT chart in your pocket. and it works really smooth. It has all the modern refrigerants. I would highly suggest it. And you can pick up that app by just searching for it. We're searching Refrigerant Slider in either the Android App Store or the Google Play Store, I guess they call that. Or if you go on the App Store inside your phone and you search Refrigerant Slider, or you can go to danfoss.com/cool apps to find it there. And then also, Jim mentions this later on, that a good way to measure the temperatures is with the Testo Smart Probes, the actual temperature clamps. They're really great clamps. They use a thermistor, and so you don't necessarily have to use it with pressure readings. You can if you want, and they do reduce losses or cross-contamination that you could get with a regular manifold set, because you don't have the hoses or the length of hoses that you have with a typical manifold. But if you don't want to use a manifold at all, you don't want to connect to the system and read pressures like Jim's talking about here, you can use temperature probes, the actual Smart Probes temperature probes, and you can take multiple readings at once, and you know that you're going to get a good level of accuracy that's going to be hard to replicate even with the typical K-type thermocouple, because they are thermistor type probe, and you can get them into tight spaces. So say you wanted to take a reading on a line actually inside the air handler cabinet, you could do that pretty easily with the Testo Smart Probes. So that's it for now. Make sure to have a good PT chart. If you don't have one in your pocket, I recommend the Refrigerant Slider. Here we go, back to Jim Bergman.
All right, so we've got up to this point where we go, okay, so we just define what design temperature difference is, and we know that for the heat quantity transfer to remain the same, the design temperature difference has to be pretty much the same across the board. So let's talk about what is a typical design temperature difference. Well, guys in the refrigeration industry, they've been using this stuff for years. This is not new, and this is why I wanted to reference the chapter of the textbook that this comes from, because I think it's really important that people understand that I'm not talking about anything here that I just came up with myself. This is things that we should know that we probably weren't taught. And one of the things I firmly believe everybody should know is, before you hook up your gauges, what should the pressures be? And if you don't know what the pressure should be, it doesn't matter what they are, right? Because think about, we use troubleshooting charts all the time, and everybody knows if you have an undercharge with a fixed orifice, let's say, you're going to have low suction pressure, you're going to have high superheat, you're going to have low subcooling, and you're going to have low discharge pressure or liquid pressure, head pressure. Yeah, right? Everybody knows that. Okay, well, the pressure's 69. Is it too high or is it too low? Right? Who knows?
Right.
You have to know what the load conditions are. All you know is it's 69. I didn't give you enough information for you to tell me, is it too high or too low? And this is where design temperature differences come into play. So this is where you can start to attentively bring up your attention here, because this is some numbers you want to get fixed in your head here so you understand how design temperature differences work. And if you're listening to this podcast on the way to your next job here, you can commit this to memory and you'll see exactly what I'm talking about when we get there. So let's talk about design for just a minute. So if the return air is 75 degrees, we're going to use 75 as our fixed point, because when you typically talk about, there's two types of design. There's AHRI design, and then there's design that we use when we're doing our manual J. AHR is 80 degree return air, 50% relative humidity, 95 degrees outdoors. Okay. And everybody knows nobody's going to be comfortable at 80 degrees. So why does AHR use that? Well, because at 80 degrees, we get a higher suction pressure, which gives us higher efficiency. They like to show the higher efficiency, so that's the way they do them. When we design, though, we have to look at extended performance tables of equipment and say, okay, what is its capacity at 75 degrees? Because we typically design for 75 degrees, 50% relative humidity at 95 degrees outdoors, at least for my area. Your area is going to change a little bit depending on your climate zone and what you're doing, right? But in general, that's what we talk about. So when we're talking about design temperature difference, by design, the evaporator coil has to be 35 degrees colder than the return air to transfer the correct quantity of heat. Now, this doesn't matter whether this is a 1 ton or a 5 ton. Okay. Why is that, Brian? I'm going to ask you, see if you know. What do we do difference between a 1 ton system and a 5 ton system? What's the major difference between the two?
The amount of airflow.
Amount of airflow, compressor size, coil size is right. You're on the right track. I'll give you a point. I would have given you a check plus in my book at school if you would have said that.
Okay.
A 1 ton system and a 5 ton system operate identical under the same load conditions, right? If we're to put a 1 ton, a 2 ton, a 3 ton, a 4 ton, and a 5 ton, they're all going to operate the same under the same load conditions because they're engineered to do the same thing. It's just moving more heat as we get larger. It's got larger surfaces and more airflow. It'll move a higher quantity of heat. This goes even if we're talking 100-ton or 700-ton or 1,000-ton machine. It's going to follow the same rules because that's the way systems are engineered. If I have a Carrier, a Train, a Lennox, guess what? If they're all 10 SEER equipment, they're all going to operate almost identical because they're moving the same quantity of heat at the same efficiency rating. And there's only so many ways you can do that. There's no magic formula for this stuff. When we talk about another myth here I want to dispel is, we talk about the efficiency of a fixed orifice versus a TXV. We always say the TXV is a little bit more efficient. Well, TXV is more efficient under a wider load of ranges. It's really at design, a TXV and a fixed orifice are exactly the same efficiency because if you were to go to a fixed orifice charging chart and look at the chart, you'd find out that the target superheat at 75 degrees and 95 degrees outside is around 12 degrees of superheat. Guess what a TXV is designed to maintain? 12 degrees of superheat. So at design, they're both the same efficiency. When we talk about the ASHRAE and we talk about EER or SEER, that's seasonal energy efficiency rating, and over the season, because we have different load conditions, that TXV is obviously going to be more efficient because it maintains a more constant superheat under a wide range of loads. But for the most part in our home, unless it gets way out of whack, we're at a pretty constant load condition. The only thing that really changes is outdoor air temp, right? All right, so...
Right. And so, to summarize, with SEER and EER, a piston and TXV system, the EERs are going to be very similar, if not identical. It's the SEER rating that you're going to see a variation between TXV and piston or fixed orifice because SEER is rating based on a wider range of load conditions.
Right, and you're only going to pick up maybe one SEER. I mean, we're not talking about huge differences here, but I just want you to understand that the metering device... It does help with the efficiency, but when it comes to the overall operation of the system, it's pretty minor different, but it will give you a little bit of efficiency. But let's go back to design temperature differences. So if it's 75 degrees, and I told you by design, the coil is going to be 35 degrees colder than the return air. 75 minus 35 is
40.
So that's our saturation temperature. Okay. So Brian, if I tell you that the superheat requirement, let's say I'm on a fixed orifice system, and my superheat requirement is 10. What's my suction line temperature going to be?
50.
Guess what?
The answer is 50, Jim.
If my suction line temperature is within plus or minus 5 degrees of 50, do I need to put my gauges on the machine?
Okay. I guess not.
Right?
Okay, all right. So how are you finding evaporator temperature, though?
How do we just find it? What's the design? How much colder is the evaporator going to be than return air?
No, at 35 degrees.
Right. So that we just said the evaporator temperature is 40.
Okay, my brain is melting here. You're just measuring the suction line temperature. But at that point, you don't know if you could be at zero superheat at that point and be at 45 degrees. And how would you know that that's what's happening and you're not overfeeding the coil?
Because once we charge the system once, all right, once you've charged the system once, and recorded the design temperature difference for the evaporator, recorded the design temperature difference for the condenser, you don't need to put your gauges on again. The design temperature difference will always remain the same, with the exception of what? What is the one thing, if you think about what is our primary job as refrigeration air conditioning technicians, the number one job above anything else, probably the thing that we don't do often enough, what would you say if we think about operation of the equipment? What is the primary thing we should be doing when we go out on a service call?
That's a really big question. That's like the meaning of the universe.
It is not. It's just a little tiny question.
How much heat are we moving? I mean, that to me is the ultimate question that we're asking.
If we're going to service equipment, here, let me ask you a question.
Okay.
All right. You got a bunch of kids. Refrigerator is not working. Milk's going bad, right? Milk's warm. All right. Kid 3, 4, and 5 complain that the milk is too warm. What's the first thing you're going to do on that refrigerator?
Check the box temperature.
Well, the milk's warm. You don't have to check the box temperature. You just spit it in the sink because you're like, oh, that is warm. It's horrible. So the refrigerator, the box is warm. So what are you going to do next?
what am I going to do next in that circumstance? Well, I'm going to go down and see if the compressor's running. I'm probably going to grab the suction line. That's probably what I'm going to do.
Really?
Next
You're not going to make sure that the door's not jarred open because the kids put the milk in wrong?
Oh, geez. Okay, sure. I'm going to make sure the door's not jarred open.
Yeah, you're not going to make sure the evaporator coil's not blocked off with some kind of bag that your wife put in with all this lettuce towards the top of the refrigerator, right? You're going to...
Sure. I'm probably going to make sure the compressor's running first. But if yes, those are things that I would do once I know
you're probably going to pull out the refrigerator and look underneath and see if there's not a whole pile of dirt and dog hair and things underneath the condenser that are making the condenser dirty, right? Seriously, I mean, think about what we do as technicians. The number one thing that we need to be doing as technicians is cleaning up dirt, okay? It's cleaning the evaporator, cleaning the condenser, cleaning the blower wheel, cleaning the secondary heat exchanger in the furnace. The heat exchanger surfaces have to be cleaned to transfer heat at the correct rate. In fact, part of a PM on every air conditioner, we should spend much, much less time hooking up our gauges and much, much more time cleaning evaporators, condensers, blower wheels, and filters and secondary heat exchangers in 90 plus furnaces. I know you guys don't have those down there, but dirt is one of the primary causes of poor heat transfer, and yet we overlook it every single day, especially when it comes to blower wheels. 1/8 of an inch of dirt on your blower wheel will decrease its efficiency. I think I've read somewhere by about 40%, right? Because think about your blower wheel for just a minute and imagine you got a baseball in your hand, right? Because that wheel is sort of cupped, right? So it cups the air and forces the air in a certain direction. Just like you have a baseball in your hand wraps around it and you can throw that ball because your hand holds it and it's very directional. Now try and hold your hand out flat and put that baseball in your hand and try and throw that baseball again, right? The ball's going to go haphazardly wherever it goes. You can't throw it. You have no direction. You might be able to get it going a little bit of one direction or another, but you've lost your control because your hand is flat now. You've taken away that form of your hand that gave it the direction and you've ruined it. Same thing with a blower wheel. When it gets full of dirt, it slaps against the blower wheel and it goes haphazardly wherever it goes. It doesn't direct itself through the heat exchanger, through the evaporator coil, or through the volute on the fan. It churns and turns and does all kinds of wacky things, but the fan loses its efficiency. And so when we're looking at this kind of stuff, the very first thing we needed to be doing is looking at dirt. So let's go back for just a minute. So once we commission, and you guys do some new installation, right?
Mm-hmm.
All right.
Whole bunch of it.
A whole bunch of it. Every system that you guys go out, you should be putting a little tag, just a little hanging tag next to the indoor part of the unit or somewhere where it's not going to get ruined, maybe in the control panel, right? And on that tag, there's a couple of things that I would highly suggest everybody always record. Number one is the design temperature difference of the evaporator. So what you do is with your gauges installed during the commissioning process, which is the only time the gauges should be installed, during the life of the system until you go to remove the system to dispose of it and put the new system in, right? I'm telling you right now, there's only one time in the entire time of the life of a system when you should put gauges on the system, and that is when you're disposing of it. The rest of the time, there's no need to unless some of these rules that I'm going to tell you here don't hold true. So follow me here for a minute because I'm telling you right now, if your refrigerator broke, you'd clean the dirt from the thing. You check the door and make sure the door's not stuck open. You check and make sure things aren't blocked off. But the last thing you do is sand the painted refrigerant lines, throw on a couple of piercing valves, and check the charge on the unit. Yet every time your guys go out for service, they're putting their hoses on there and checking the charge of the unit. And every time they go out for service, their 410A lines that they've had open to atmosphere in the back of their truck that are coated with POA oil, have absorbed all kinds of moisture, are contaminating that system and putting moisture into your system and contaminating your refrigerant charge. And every time they connect and disconnect their hoses, they're losing a little bit of gas. And in a year or 2 or 3 years later, you're chasing around a leak that doesn't exist because your guys have been dumping gas out of the machine inadvertently instead of not putting their gauges on the machine, which is actually the correct practice. All right?
Preach it, brother.
I'm telling you, this stuff drives me crazy.
You're getting fired up. You're getting fired up. I like this. This is good.
When you're checking that, design temperature difference of the evaporator, design temperature difference of the condenser, total external static pressure. We want to see if that total external static pressure is changing. Pressure drop across the filter when you install it. So you understand that when that homeowner goes out and buys that 3M, nothing gets through this filter, including air, that the static pressure has increased significantly across your filter. And maybe there's your problem, right? We need to, what I call, benchmark the system performance. When we benchmark a system, we have certain information at our fingertips that tell us how that system's running today versus how it was running the day it was commissioned.
All right, so I'm going to go ahead and leave you hanging there. We're going to publish part 2 of this episode, the part 2 of the checking charge with no gauges, where we get into a lot more of the specifics later on this week. So stay tuned for that. As always, thank you for listening to the podcast. If you don't subscribe to the podcast on your phone, then I would strongly suggest that you do that. If you have an Android device, look up the Stitcher app and subscribe to the podcast there. All you have to do is just search HVAC. Also, if you have an Android, or I'm sorry, if you have an iPhone, you can do that by going to the podcast app on your phone. Or if you go to hvacrschool.com, that's the homepage. You can look, I don't know, just a little bit down the page, and there's a link right there where you can subscribe. So if you pull that up on your phone, just open your browser, look up hvacrschool.com, scroll down just a little bit, and there's a couple buttons for you to subscribe, whether you're an iPhone user or an Android user. So thank you for being here. We'll see you again a little later this week to finish up this full episode on checking charge without gauges. See ya.